right now, somewhere in this universe, a star 30 times the mass of our Sun is about to die. And when it does, it won't just fade away quietly. In less than 1 second, its core will collapse so violently that it punches a hole in the fabric of reality itself. A region where gravity is so extreme that space curves in on itself, time slows to a crawl, and anything, absolutely anything, that crosses a certain invisible boundary will never come back. Not light, not information, not even the laws of physics as we understand them. That is a black hole. And here's the thing that keeps me up at night. We used to think these were rare, exotic curiosities tucked away in the most extreme corners of the cosmos. We were wrong. There could be 40 quintillion of them out there. That's a 4 followed by 19 zeros. And they are not just sitting quietly in the dark. They are building galaxies, devouring stars, bending time, and as of this year, revealing secrets we never imagined possible. So, let's go on a journey. From the moment a black hole was nothing more than an embarrassing mistake in Einstein's math, all the way to the cutting-edge discoveries of 2026 that are genuinely rewriting what we know. And I promise you, by the end, the way you look at the night sky will never quite be the same. Let's start at the beginning. And I don't mean the beginning of black holes. I mean the beginning of us even imagining they could exist. Because for a long time, nobody wanted them to be real. The year is 1783. An English clergyman named John Michell writes a letter to the Royal Society, and in it, he proposes something that sounds almost ridiculous. He suggests that a star 500 times the mass of our Sun would have gravity so powerful that even light could not escape it. He calls it a dark star. And then, for over a century, the entire scientific world basically shrugs and moves on. Fast forward to 1915. Albert Einstein publishes his theory of general relativity, this beautiful framework that reimagines gravity not as a force, but as a curvature in space-time caused by mass. It was revolutionary. It was elegant. And buried inside the mathematics was something Einstein himself did not want to find. Just 1 year later, a German astronomer named Carl Schwarzschild, while actually serving on the front lines of World War I, solves Einstein's equations for a single concentrated mass. And what falls out of the math is terrifying. There is a radius, a boundary, beyond which gravity becomes so overwhelming that nothing, not matter, not energy, not light, can ever climb back out. Schwarzschild dies just months later, never knowing that he had described the anatomy of a black hole. But here's the part that I find genuinely fascinating. Einstein hated it. In 1935, he published a paper saying, and I'm paraphrasing here, that singularities bring so much chaos into the theory that they basically cancel out the laws of physics. And then, in 1939, he went even further, publishing a paper explicitly arguing that black holes were impossible. He believed some unknown force would prevent a star from collapsing that far. And on the exact same day, September 1st, 1939, the very same day that Nazi Germany invaded Poland and World War II began, a physicist named J. Robert Oppenheimer published a paper proving Einstein wrong. Oppenheimer showed mathematically that a massive star absolutely will collapse completely, punching through that Schwarzschild radius and forming what we would later call a black hole. But because the world was, understandably, a bit distracted that day, the paper was basically forgotten for 20 years. Think about that. The moment we proved black holes were inevitable was the same moment the world descended into its darkest chapter. Oppenheimer's paper sat in obscurity while he went on to build the atomic bomb. The universe has a strange sense of timing. Now, the name black hole did not even exist until 1967, when the physicist John Wheeler finally coined the term during a lecture. Before that, scientists called them frozen stars, or gravitationally completely collapsed objects. You can see why the catchier name stuck. And it wasn't until 1971 that we actually found one. Cygnus X1, a system about 7,200 light-years from Earth, where a blue supergiant star orbits an invisible companion roughly 21 times the mass of our Sun. The first confirmed black hole, and the subject of a famous bet. Stephen Hawking wagered against its existence. He called it an insurance policy. If black holes turned out not to be real, at least he'd win the bet. He conceded in 1990. But here's a question that should make you pause. If black holes are born from dying stars, then what about the very beginning? What about the Big Bang? See, when the universe was less than a second old, it was unimaginably dense. Every particle in existence crammed into a space smaller than an atom. And in 1966, Soviet physicists Yakov Zeldovich and Igor Novikov proposed something wild. They suggested that in those first fractions of a second, some pockets of matter were so concentrated that they collapsed directly into black holes without ever forming a star at all. Stephen Hawking expanded on this idea in 1971. These are called primordial black holes, and they could range in size from the mass of an asteroid to the mass of a moon. For decades, this was just a theory, a beautiful, elegant, but completely unproven theory. And then something happened. On November 12, 2025, LIGO, the gravitational wave observatory that spans 2 sites across the United States, detected a signal. It was catalogued as S251112cm. And when scientists analyzed it, they found something that stopped them cold. At least one of the objects involved in this collision weighed less than a single solar mass. Now, here's why that matters. No known process in the universe can create a black hole that small from a dying star. The physics simply doesn't allow it. There's a hard limit, called the Chandrasekhar limit, at about 1.4 solar masses. Below that, a star just doesn't have enough mass to collapse into a black hole. So, if this object really was a black hole, and the evidence is very strong that it was, then it could only have formed one way. In the first moments after the Big Bang, before stars, before atoms, before the universe as we know it even existed. Nico Cappelluti from the University of Miami put it plainly when he said, "We believe our study will aid in confirming that primordial black holes actually do exist." And it gets even stranger. In 2023, a detector called KM3NET, an underwater telescope in the Mediterranean Sea, captured a neutrino with an energy level that should have been impossible. About 100,000 times more powerful than anything the Large Hadron Collider has ever produced. 35 times more energetic than any neutrino ever detected before. And there's no known source in the universe that can create that kind of energy. But physicists at MIT and the University of Massachusetts Amherst proposed an explanation that gave the entire field goosebumps. That neutrino, they said, may have come from a primordial black hole in its final moments of existence, exploding in a burst of something called Hawking radiation. David Kaiser at MIT described it perfectly. He said, "You'll never, ever hope to see Hawking radiation if the only black holes ever were ones that formed from dead stars." Primordial black holes have different masses and different lifetimes. Some go bang right now. If this is confirmed and the research is ongoing, it would be the first experimental evidence of Hawking radiation, the first direct proof that primordial black holes exist, and potentially an explanation for dark matter, all from a single particle hitting a detector at the bottom of the sea. That's three of the biggest open questions in physics, potentially answered by one ghost particle. But let's come back to the black holes we know best, the ones born from stars. When a star at least 20 to 25 times the mass of our Sun exhausts its nuclear fuel, the outward pressure that kept it inflated for millions of years simply vanishes. And in less than a second, the core collapses. The outer layers are blown off in a supernova, one of the most energetic events in the universe. And what remains, if the core is heavy enough, becomes a black hole. Now, what does a black hole actually do to the universe around it? Because they don't just sit there. This year, astronomers measured something nobody had ever measured before. Using 18 years of radio data from a planet-sized network of telescopes, a team led by Steve Prabhu tracked the jets erupting from Cygnus X1, that very first black hole we ever confirmed. And they found that those jets carry the energy of 10,000 suns and travel at roughly half the speed of light, 355 million miles per hour. And 10% of all the energy released as matter falls toward the black hole, gets channeled directly into those jets. Think about that. A region of space smaller than a city, generating as much energy as 10,000 stars and firing it across light years like a cosmic fire hose. And then there's Galaxy J, 1007 plus 3, 540. Where a supermassive black hole at the galaxy's core went silent for nearly 100 million years, just dormant, sleeping. And then it woke up. New jets erupted, stretching nearly 1 million light-years across space, slamming into the surrounding galaxy cluster like a cosmic volcano. 100 million years of silence, followed by an explosion that spans distances our minds can barely comprehend. But perhaps the most disturbing thing a black hole can do is eat. When a star wanders too close, the difference in gravitational pull between the near side and the far side literally stretches it into long, thin strands, a process scientists actually call spaghettification. The star is pulled apart like taffy, its materials spiraling into a superheated disk that can outshine entire galaxies. We call this a tidal disruption event. And earlier this year, astronomers observed one where the black hole kept ejecting material for years after the star was destroyed. Years. As if the black hole was still burping from a meal it finished long ago. Now, here's where it gets philosophically unsettling. What is actually inside a black hole? According to Einstein's equations, at the very center is something called a singularity, a point where all the mass is compressed to zero volume and infinite density. A place where the laws of physics, every equation we've ever written, break down completely. It's not a place in space. It's more like a moment in time. Once you cross the event horizon, the singularity is not ahead of you in the way a wall is ahead of you in a room. It is in your future. You cannot avoid it any more than you can avoid next Tuesday. But most physicists suspect the singularity is a sign that our theory is incomplete. That when we finally figure out how to merge gravity with quantum mechanics, the singularity will dissolve into something else. Maybe a Planck star, an incredibly dense but finite object predicted by loop quantum gravity. Maybe a fuzzball, a tangled knot of quantum strings predicted by string theory. Nobody knows yet. And that beautiful, maddening uncertainty is part of what makes black holes so captivating. And there's another puzzle. Hawking showed in 1974 that black holes are not actually eternal. They slowly radiate energy and lose mass through a quantum process now called Hawking radiation. A black hole the mass of our Sun would take roughly 10 to the power of 67 years to evaporate. That's a 1 followed by 67 zeros. The universe itself is only about 13.8 billion years old, so we're talking timescales that make the age of the cosmos look like a blink. But here's the heartbreaking part. That radiation appears to be random. It seems to carry no information about what fell in. And quantum mechanics insists that information can never be destroyed. So either quantum mechanics is wrong, or general relativity is wrong. Or there's something deeper going on that we haven't figured out yet. This is called the black hole information paradox, and it remains one of the deepest unsolved problems in all of physics. Even Hawking himself conceded in 2004 that information is probably preserved, but we still don't know how. And just when you thought it couldn't get more mind-bending, 2026 delivered one more revelation that genuinely shook the field. A team of researchers published a study in the monthly notices of the Royal Astronomical Society, arguing that Sagittarius A star, the 4 million solar mass object we've been calling the supermassive black hole at the center of our galaxy, might not be a black hole at all. They propose it could be an ultra-dense clump of dark matter made of lightweight particles called fermions, forming a compact core that mimics a black hole's gravitational effects so perfectly that even the famous Event Horizon Telescope image is consistent with their model. Valentina Crespi, the lead author, said the dense dark matter core could bend light so strongly that it creates a central darkness surrounded by a bright ring. Exactly what we photographed. Now, this is not yet the consensus view. It's a provocative alternative supported by new data from the European Space Agency's Gaia mission. But it raises a question that honestly gives me chills. What if the thing we've been staring at for decades, the object we built an Earth-sized telescope to photograph, isn't what we thought it was? What if the boundary between what we know and what we only think we know is thinner than we imagined? And maybe that's the most important thing about black holes. They are not just objects in the sky. They are mirrors for our ignorance. Every time we think we've understood them, they reveal another layer of mystery. They were predicted by equations their creator didn't believe. They were proven inevitable by a paper nobody read. They were named by a man who initially doubted them. And now, in 2026, they're being redefined by signals from the very first moments of the universe. We are alive during the single most exciting era in the history of black hole science. The era when we went from imagining them to photographing them, from theorizing about their radiation to potentially detecting it, from assuming they were simple to discovering they might hold the key to dark matter, quantum gravity, and the origin of the universe itself. And every time you look up at the night sky, just know that scattered among those points of light are regions where space-time has folded in on itself so completely that not even the universe can see what's inside. Pockets of infinite mystery hiding in plain sight. If this video made you look at the cosmos a little differently, I'd love it if you subscribed to the channel. Drop a comment telling me which discovery from this video surprised you the most. Was it the possible primordial black hole signal? The neutrino from an exploding black hole? Or the idea that Sagittarius A star might not be a black hole at all? And if you know someone who'd love this, send it their way. I'll see you in the next one.